Okay, I hope you can see my screen.
Yes, sir.
Okay, good. So we have started with deterministic, non-deterministic, finite automata and the class of languages that they accept. So these are the so-called regular languages, and after that, uh, my co-teacher introduced so-called context-free grammars, which essentially define a bigger class of languages called the class of context-free languages. And you have also seen examples that this class is not all-encompassing. So there are languages which are not even context-free. Now, we have essentially studied only context-free grammars, parse trees, and all that stuff. We have still not seen machines that can accept context-free languages. This is what I will cover in this week and maybe a part of the next week. So these machines are called, okay. Push-down automata, or in abbreviated form, PDA. Okay, so this push-down comes from what is called a push-down store, and you know it in a different name called stack. Okay, so you can also call them stack automata, but somehow people prefer this PDA, push-down automata, this terminology, this term, better than stack automata. But you can call it stack automata. It's not a very big issue. Okay. So what happens in case of a finite automata, you have a situation like this. You have a kind of CPU consisting of several states. Okay, and that is basically our queue. And also some rules how you transfer from one state to another. Okay. And you have a read-only input tape. Okay, so this is read-only input tape where you specify the input and the machine keeps on reading symbols one by one. And if you allow epsilon transitions, then in some cases, you may skip reading anything from the input, but make some automatic transition. That is epsilon NFA and all that stuff. Okay. So whatever these simple machines can remember is by using its states. This is a read-only tape. Not only that, it can read it only once, and reading happens only from left to right, from beginning to end. Okay. But before making any final decision, the machine will have to read this entire input. Okay. Now, because the amount of memory is very much restricted to whatever the CPU can store in the form of states, we have seen that this is a very primitive class of languages. Okay. What from now onward we will do is that we will give some external memory alongside this basic framework. So this is an external memory. And whenever we talk about push-down automata or stack automata, this external memory is organized in the form of a stack. Okay. So in addition to a finite set of states and the read-only input tape that has to be read sequentially from left to right or from beginning to end, you have an external memory that is organized in the form of a stack. Okay. So stack means there is something that can access this stack. Okay. And this is the top of the stack. And this is called the bottom of the stack. And this is a hypothetical stack having no restrictions on how big it may grow. Okay. So this is essentially supplied to the machine as an external memory so that the machine can do some rough work here. Okay. It can store counts, do some other things, it will remember certain things. And you can see that this memory is infinite because this stack can grow as, I would say, as much as it can. Okay. So now that I have given this external memory to store certain information that the machine requires, we will see that the class of languages has become strictly larger. In fact, we will see that a machine of that form is exactly addressing the class of context-free languages. Okay. And then there is also some acceptance or rejection criterion. So like either like push down or like finite automata, there may be some green button for acceptance, and there may be some red button for rejection. Okay. The important thing you must understand is that I will talk about how this machine accepts or rejects. Okay, there are actually two ways of doing this. One thing is that the machine always starts in a start state, and this initial stack configuration is something very special. Okay. And the machine keeps on reading symbols from the input one by one from beginning to end. So this is one important thing. It must read the entire input before taking any decision. Okay. So after reading a partial fraction of the input, it does not take any decision. So it has to read the entire input. So you must remember this part. And now transitions are depend on three things. Three things. One, the input symbol. Okay, no, maybe I start with the current state. Okay. If it is P, then like finite automata, input symbol that is currently read by the input head, read only head. And from beginning, we will allow epsilon as an input symbol. Of course, allow epsilon as an input symbol means that the read-only input head stays there, reads no, I would say, reads no physical symbol from the input. Okay, and that is essentially equivalent to saying that it reads epsilon from the input. So we will allow that. Epsilon transitions are allowed. The third thing is that the symbol at the stack top. Okay. Every, I would say, transition of this machine takes care of these three things. Current state, the input symbol, which may be empty, and the symbol just sitting at the top of the stack. Okay. So these are the three inputs for the transition function, and the output is a new state. Although I say new, it may be the same as the old state. Okay. So new is within quotes. And then what the machine does, it replaces the top stack by a sequence of stack symbols. Okay, I will formalize these things later. So if that sequence is an empty sequence, that is equivalent to pop. Okay. And if that sequence is the same as the symbol that the machine scans from the stack top, and it means you just keep the stack unmodified. Let it be as it is. And if it's something new symbol, it means that new sequence. Okay, that means you just remove the stack top, pop it, and then push this sequence to the stack. Okay. So this is how this machine essentially works. Okay. So I once again reiterate that because the machine can store technically an infinite amount of information in this external memory, now the machine can accept a bigger class of languages than regular languages. This external memory is very, very important. And when we talk about context-free languages, context-free grammars, push-down automata, we will access this external memory in a very restricted fashion. Although this is infinite memory, you have to access only the top of the stack. Whatever is below that, machine cannot access it before popping it out. Okay. That is how a push-down automaton works. Okay. A very broad description. What now I would like to formalize is that how I can then specify such a machine. Okay. So a push-down, okay. There is another important thing. So first of all, we have allowed epsilon transitions, right? And another thing is very important. By definition, PDA are non-deterministic. Okay. So earlier we started with deterministic finite automata and generalized the concept to non-deterministic finite automata. But whenever I say PDA without any qualifying adjective, whether it is deterministic or non-deterministic, I mean that it is a non-deterministic machine. And if I want to highlight that we are dealing with non-deterministic machines, people may also use something called NPDA, non-deterministic push-down automata. But for us, PDA is same as NPDA. Okay. Later, I will try to cover a little bit on the so-called deterministic push-down automata. It's deterministic. And we will see that this DPDA are in some sense less powerful than this PDA or NPDA. Okay. So we will come to that later if time permits. I hope I can just give you a brief 1 hour or half hour exposure to this deterministic push-down automata. Okay. So to start with, you never forget that epsilon transitions are allowed, and by definition, these are non-deterministic machines. Okay. Okay. So given this, I formally define such a machine as M, Q. I will one by one explain everything. Sigma, gamma, particular symbol, and then I have delta, S, F. It's essentially a 7 tuple. So this is a, okay, maybe I come here, a finite set of states. Okay. So like DFA, how many states the CPU can be in? So that is basically characterized by Q. Sigma is the input alphabet, the same as in the case of regular languages or deterministic finite automata in general. So this is the input alphabet. Okay, the symbols from which these strings are composed. Okay, so that is the input alphabet. And then I am also dealing with something called the stack. So each cell in the stack is considered to be a symbol. Okay. And that alphabet, whatever symbols can be there at the top of the stack, that is what is meant by this gamma. This is the stack alphabet. It may have certain things in common with the input alphabet, but it may use other symbols and so on. We will see examples.
Excuse me, sir.
Yeah.
So just each cell of the stack will have a sequence of characters or just one character?
No, stack is always a sequence of characters.
So sir, each cell of it.
No, each cell is only one character. Only one character. Yes. Each cell is only one character. Yes. Yeah. So the top of this stack is a character, is a symbol. It's not a string. Okay. But whatever you are replacing that with, that may be a string of stack symbols. Okay. This is something called the initial bottom marker. Okay. So why it is needed, I will come to that a little later. And this is the start state. This is a set of final states. We will see that depending upon how the machine accepts or rejects, this F may even be empty. Okay. Anyway, we will come to that a little later, slowly, one by one. And this is the so-called transition function. Okay. So that defines this machine. But how are our transition functions now defined? So I would say, what is the input of the transition function? Set of states. Okay, a state is needed. And then you have sigma union epsilon, because epsilon transitions are always allowed. And then you consult the symbol at the top of the stack. Okay. And so this essentially, you may actually write it as in the I would say, Cartesian product form. One element here, one element here, one element here, and the output will be another state Q, maybe the same, and an arbitrary string over gamma. Okay. And I told you that this is not a function, because for every individual input coming from this set, there may be multiple possibilities, there may be 0 possibilities, because we are dealing with a non-deterministic machine to start with. Okay, so this is the input part, this is the output part, and delta is basically a relation, a subset of this set. Okay. Not only that, you see that this set, this is a finite set, right? Q is a finite set of states. This is input alphabet is finite. I'm just adding extra one symbol. Gamma is also a finite alphabet because every alphabet is finite by definition, but this gamma star is not finite. Okay. But the point is that the transition entries, okay, that are present in this delta, they cannot be infinitely many in quantity. Okay, so I would say this is a finite subset of this. Agree? Because gamma star is infinite, I have infinite subsets of these Cartesian products, but for a machine to work, we cannot have an infinite specification, so it has to be a finite subset of this. Okay. Okay.
Sir, I have a question.
Yeah.
The stack, can it ever be empty?
Yeah, I'll come to that. Okay. That thing I have actually missed. So the way I have defined this, okay, it says that for every transition, I not only need a state and something from the input or epsilon, I can ignore symbols from the input, but I have to read at least one symbol from the top of the stack. Okay, so M cannot proceed with the stack empty. Yes. Okay. So the stack can be empty only at the end. Okay. That is important.
Okay, sir.
Yeah. It can be empty only at the end, and actually we'll see that what empty stack means for certain machines. Okay. This is a very important realization that the stack cannot be empty. If the stack becomes empty, the machine can no longer proceed. It gets stuck. Okay. So that is the case of rejection. Okay. So the stack can never be empty. So in particular, it says that for the machine to start working, the stack can also be, it cannot be empty, right? So what I do, I initialize the stack with this initial bottom marker. It's a symbol from gamma, okay? So for the machine to kickstart its operation, the stack cannot be empty. So that is the reason I supply this initial bottom marker. Then whatever the machine does with this bottom marker, it keeps it there. It removes or replaces it by something else. That depends on the machine. Okay. But for the machine to start working, we must have something sitting in this tab, and that is the initial significance of this special symbol from gamma. Okay. Or to be more precise, the machine starts working this way. Okay, so start. So the state is S. Okay. Entire input is waiting to be read. So this is W. So this head is positioned here. And stack is initialized to this. Maybe I will just redirect this to point to this. Okay. And then one by one symbols or epsilon are read from the input. Stack is modified. And when this entire input is read, then the machine will have to take a decision whether it is going to accept the input or not. So what is the final thing? So this is the start, beginning, this is the end. Okay. So there are two ways a PDA can accept. Okay. So two, I would say, modes of acceptance or rejection, the final decision basically. Okay, so one mode, so by entering a final state that is a member of F. Okay, so rejection, let us, two modes of acceptance by entering a final state, and when after this entire input is read. Okay. And in this mode, if the machine goes to the final state, it does not look into the stack. It may be empty, maybe non-empty, whatever it is sitting there, that is not important. Okay. So stack may contain anything in this mode. It may even be empty. And the second mode of acceptance is by emptying the stack. And if that is the mode of acceptance, there need not be any final state. Okay. So in this case, F may be empty. If I process the entire input, do some scratch work on the stack, and eventually if I can completely empty it, after I have read the entire input, process the entire input, if I can do that, I say I have accepted. And in this case, the final state plays no role, so I can take F equal to empty. Okay. So tomorrow, I hope, yeah, of course, tomorrow, because it's a 2-hour class, I will show that these two notions of acceptance are essentially the same. In other words, what I will prove that given any machine which accepts by final state, given any other machine that accepts by empty stack, I can always convert that machine to a machine which accepts both by final state and by empty stack. Okay. So this notion of acceptance is not, I would say, as specific as in the case of finite automata, but it doesn't really matter, except when you design some push-down automata. So you have to say that I want my machine will accept by final state, or you say I want my machine will accept by empty stack. Without you specifying that thing, your construction becomes incomplete. Okay. So this is how this machine works. And it has these components, Q, sigma, gamma, bottom marker, delta, S and F defined this way. Okay. So I do not have enough time left today. So what I will do, I will give you an example, or maybe if time permits, a couple of examples of how such machines can be built to accept certain context-free languages. Okay. So example, okay. Example 1. Okay. But before I draw a machine, I just mentioned that this delta function has 3 inputs, 2 outputs. Okay. So every element of delta is of this form, P, A, and A may be epsilon. What is that? Some stack symbol, capital A, let's say. Output is Q. And some string over the stack alphabet. And I may call it, let's say, gamma. Okay. So in picture, what I do, I have a state P, I have a state Q. Of course, if P is Q, then this is basically an arc. There is a transition from P to Q, P to Q. It is triggered by A, also by A, and A is replaced by gamma. So this is the pictorial thing that I will use. The transition from P to Q, initiated by A as an input symbol, maybe epsilon, and the stack top symbol A, and the effect is going to state Q and replacing that A by the string gamma. Okay. So if gamma is something like B1, B2, Bk, stack was something here like this, A was sitting there, that is replaced by B1, B2, Bk. Okay, so B1 will be the new top. That is the convention. It is not B1, B2, Bk this direction. It will be B1, B2, Bk. So this will be my new top. And if K is 0, this essentially means A is popped out and the stack top becomes one step down. Okay. So K may be 0, K may be 1, K may be 2, but there are only finitely many possibilities. Okay. So with this understanding of our notations or pictorial conventions, let me first design a PDA for this. Okay. So what the PDA will do, it will initially keep on absorbing these A's, and it will remember in the stack how many A's it has read. Then it will switch to another state which processes the B's. So it will keep on reading B's, and for every B that it reads from the input, it will throw away one A or something like that it remembered in the stack. Eventually, if I would say the counts match, counts of A's and counts of B's, count of A's and count of B's, they exactly match, then at the end, only the bottom marker will be exposed. So it will then make two things. When the input is completely ready, completely read, it may ignore whether this bottom marker is there, but it should be there. Go to a final state and accept. Another option is it will simply pop that bottom marker, empty the stack, and accept. Okay, so let me draw this. This is the start state, essentially meant for processing this, reading this initial part of A, and I will actually make it a deterministic machine. In fact, this is a deterministic context-free language. But anyway, for the moment, let's not worry too much about determinism. Okay, so A has come, and initially the bottom marker is there. So I will just store this A in this stack. Okay, so I will say, okay, you stay there. Bottom marker, you stay there. I am just pushing an extra A. Okay. But once after I have pushed one extra A, this bottom marker is no longer exposed. So if I see A at the top of the stack, I will push another A. Okay. This part is clear. As many A's I am reading, the machine is reading from the input, those many A's are pushed to the stack, and the bottom marker stays at the bottom. Happy or not?
Yes, sir.
Okay, good. Then the machine makes this epsilon transition. If A is there on the top of the stack, just keep it. If the bottom marker is at the top of the stack, keep it. Okay. So when is this still exposed? If no A's are read. If n is equal to 0, then this case will happen. Okay, it makes this epsilon transition, comes to this state. Okay. Now it keeps on reading these B's. Okay. But for every B that it reads, there must be one matching A sitting in the top of the stack. Without that, it gets stuck. So if it reads B, if it finds the corresponding A, just pop. If it happens that the bottom marker is exposed and there are still more B's coming, then the machine gets stuck. And it's essentially a case of rejection by getting stuck. Okay. We should also handle the case when the number of A's is more than number of B's. Okay, it's possible that there are 10 A's, only 5 B's. So 5 A's are neutralized by these 5 B's. The remaining 5 A's are still sitting there in the top of the stack. Okay, in the stack. So that case I have to handle. Now, if the machine decides to accept by going to final state, I can do it something like this. After the machine is done with reading all the sequence of B's, and if there is an exact match of this count and this count, what should be exposed? The bottom marker, right? So if the bottom marker is exposed, input is entirely read. Keep it there, or doesn't matter. Go to this final state and accept. Here you see, there is no provision. There is no provision for reading any input. So this transition should happen only at the very end, after the entire input is consumed, because the inputs are consumed here and here. Okay, so if some part of the input is still left, okay, then the machine will not accept, because yeah, some part of the input is left. Okay, the decision is always with respect to when the machine has processed the entire input. Okay, so this is acceptance by final state. Okay, so the machine could have also accepted by emptying its stack, and that happens this way. If it sees the bottom marker exposed, pops it, goes to this state. So this is acceptance by empty stack. Okay. A bit by mistake, it ever empties this, and some B's are staying in the input, then this is not acceptance. And if this acceptance is by empty stack, there is no point making it a final state. I can additionally call it a final state, but anyway, that doesn't matter. Okay, so do you understand the difference between these two, acceptance by final state and empty stack? It can empty stack if and only if the counts of A's and B's exactly match. Otherwise, it cannot have this bottom marker exposed at the end of the input string. Happy? Yes or no?
Yes, sir.
Good. Okay, so what I will do, I will just introduce another language. I will construct the PDA tomorrow because I have just 5 minutes left. Example 2. Again, if this is this language you have encountered earlier, let's say AB star, such that number of A's in W is equal to number of B's in W. Okay, so I will draw the PDA for this later, but let us. Is this covered in your first few hours? What is the context free grammar for this? Is it covered? Balanced parenthesis is covered, I know. You do not remember. Anyway, forget it. Okay, so first I will draw a CFG for this, or derive a CFG for this. Okay, so for any string S, W, or X, let me define the surplus of A's in X minus the surplus, number of A's in X minus the number of B's in X. So that is the surplus of A's over B's. Okay. So if I now draw a graph of this surplus function, so X basically, this is the entire W. Okay. And this is the surplus function, S values. Initially, the surplus is 0. Because nothing is red, number of A's is 0, number of B's is 0. And eventually, it should also be 0. If the number of A's and number of B's in W are the same. And here you may have something like this. Okay. Starting from 0, it should end in 0. Okay. So I consider 3 cases, let's say. W starts with A, followed by something, Y, ends in B. Then what will be this Y? This will also be a member of that language, right? In total, there are exactly equal number of A's and B's, but W starts with A, ends with B, so whatever is in between, it must be consisting of again an equal number of A's and B's. Similarly, this is the case. Okay, but I may have a situation something like this. So this Y is once again belonging to this. But I may have situation like this, A, B, B, A. Okay, starting with A, ending with A, but still contains equal number of A's and B's. Now if I look at that graph here, the start symbol is A, the surplus will become A. Eventually I will reach 0. But by again reading an A, I must be coming from here. Agree? And if I now look at the surplus function, it is something like a continuous map. After every step, it either increases by 1 or minus 1. Okay, so increases by 1 or decreases by 1. So if the curve is something like this, starting from 0, it goes to 1, and it eventually reaches 0 from minus 1, then there must be some intermediate point where this curve will cut this axis somewhere. You cannot avoid it. You cannot jump it. Okay. Therefore, the context-free grammar is something like this. S can be epsilon, no problem. ASB or BSA. And the final case is this SS. Okay. From this point to this point, it's an instance of this language where there are equally many A's and B's. From this point to this point is once again another second instance of substring where there are equally many A's and B's. Okay. So this essentially gives you a justification why this grammar for this language is correct, both sound and complete. Okay. So what I will do tomorrow to start with, I will design a PDA that will essentially keep track of this surplus function in its stack. Okay. Okay, so we will do it. Okay, so any questions today?
So can we just add the surplus A's or B's to the stack and when it's empty?
It's not difficult. You should be able to do it. Many of you should be able to do it, but we will do it as an example. Okay. Okay, so let us stop today.
So one more thing, if we are reading a string and when we have not finished, the stack becomes empty, so it is rejected, right?
Method gets stuck.
Okay, sir.
Yes.
Thank you, sir.
It should be empty only after the entire input is processed.
Okay, sir. Thank you.
Okay, so any other questions? If not, let us stop today.
Thank you, sir.
Thank you, sir.
Okay, bye.
Thank you, sir.